So we continue our discussion on calculus, which is our unit 2. Okay, so here are some total 14 lectures are allowed. Okay, so the topics that we have, starting from Taylor's theorem to we have Lagrange's method of multipliers. So, okay, these topics are very important for your engineering courses, and maybe if you study, there are some numerical solution of differential equations. For example, this Taylor's theorem, these concepts will be useful if I think it is in the sixth semester. Sixth sem, there is a open elective mathematics paper which is called NSTE, or numerical solution of differential equation, and in the seventh semester these two concepts will be useful when you choose. There is another open elective mathematics paper, is called optimization techniques. So these concepts will be useful. So that is why go through it properly. I mean, if you have doubts, you must ask me. Otherwise, later it won't be easy to follow. Not only that, okay. So these concepts, other concepts, you may find at some stage of your 4 year of BTech course. Okay. So that is it. Each concept is important. Whether each are interesting, that depends on the topic, and also, of course, it is on the representation. But yes, no topic is useless. Every topic is important. Now, if we just recall our high school mathematics, so we have seen that Rolle's theorem, if a continuous function is defined on a closed interval AB, and if the derivative exists on that open interval AB, also with the condition that f of A equals to f of B, if these three criteria are satisfied, then there is at least one point C in this open interval, so such that if the C is equals to 0, that means the slope will be parallel to the x-axis. That's what we have seen in our high school mathematics. Now, to generalize this concept, we have seen the Lagrange's mean value theorem. Okay, so where we consider a continuous function in the closed interval AB, and then we say we have defined that if dash x, that is the derivative, exists in the open interval. If such happens, if these two conditions are satisfied, then we can write f dash c equals to f of b minus f of a. So c is in between the starting point and the end point of the open interval. Now, if you write this equation, if we simplify this, then we get f of b equals to f of a plus f dash c into b minus a. Now, instead of this b, if you suppose f of x, we write in place of b, we write x. That is, x is a variable. Instead of fixed point a to b, if we write that x, suppose you try to change the variable. So what will happen? So that remains f of a plus f dash of c into x minus a. Now you can see that x minus a is a polynomial of 1 degree. There is a power of 1 degree is there. Okay. Now this concept will be used just after some introduction of two examples. So, also, we want to generalize the concept for higher order derivatives. So what will happen instead of this first order derivative? What will happen for second order derivative? What will happen for third order derivative? And so on. Okay. Then the expression, what will be the expression for this case? And how we will use in our practical problems. So just for a starter, let us suppose f of x equals to e to the power x. For x equals to 2, we know that this value will be approximate value will be 7.389. Now, if you write this is P1, this expression is P2, okay, and then this is P3. Similarly, P4, P5, then P6, P7, and then P8. So what we see, if we can write some systematic expressions, okay, so then what we get is actually approximate value. So this value and this value are actually almost similar. So the gap actually becoming tends to 0. Yes, this is expression of e power x. There is no surprise because you all know. Now, if I write that Pn P8 of x, there is a polynomial of 8 order. Polynomial. There is a Pnx. Okay, polynomial of nth order. Okay. So for a given function, suppose we don't know this function. Okay, so this is an arbitrary function. But can we find such polynomials for which that Pnx, Fnx, f of x will be approximated by some Pnx? Suppose we don't know the function has expression. So there we have some fundamental polynomials, for example, e power x, cos x, sin x, 1 by 1 minus x, then log 1 plus x. So these are some fundamental polynomials we know. With this knowledge, basic knowledge, we will try to approximate a given function using the polynomials. Instead of this, if you write this polynomial, what it would be? Polynomial. So this polynomial will be 8th order polynomial. So 1 plus, in place of 2, you will write x plus x square by 2 factorial plus x cube by 3 factorial and so on. Okay. Now, if we have a different polynomial, different function fx, then what happens? We try to approximate the function that fx is the red curve. This is cos x. Okay. Now, at x equals to 0, we try to approximate this value. In the neighborhood of 0, for example, 0 minus epsilon to epsilon plus 0. So 0 plus epsilon. Okay. That means here it is 0. Then you take some epsilon greater than 0 minus epsilon, where epsilon greater than 0. Okay. You take this interval, we call it a neighborhood. And then what we want to approximate, that is P and X will be almost equal to the value of cos X. So, okay, if you take fourth order polynomial, for example, if you take two order polynomial, then what happens? This red curve and this blue curve is actually matching these values up to here. But if you take a fourth order polynomial, then you can see that the interval, this interval has increased, for example, minus 2 epsilon by 2 epsilon. If you take further sixth order polynomial, then this is also increased further more. So that means the polynomial is matching the value of fx, the given function, a more number of points. But if you think eighth order polynomial, then you can see that this is, in fact, this will be minus 3 to plus 3. So we have started with this much. Now we are getting this many points, minus 3 to 3. There it is matching out the point. Okay, just a graphical representation. If you try to look at this, for example, if you look at the function y equals to fx, so this is the blue line. Okay, and then we try to look at the approximations of the function. First, we take the P2, that is the second order polynomial. So it is matching over, for example, minus 1 to 1. Okay. At 1, you will see that at x equals to 1, the polynomial P2 will have the value as 0.5. But at cos 1 will be 0.543. Now, if you improve, I mean the sixth order polynomial, so it is matching more number of points. But if you take that eighth order polynomial, then we can see that this is from minus 3 to plus 3. It is matching this many values. Okay. But if you zoom it, you will see that the difference between these two curves will be 0. It is tending to 0 actually. So this is what we call it approximation. So given a function, we are trying to approximate by some known polynomials. Okay. Now if you look at x equals to 1, okay, if you try to look at the function, I will tell you this. So here, okay, let me just take this snap. And so what happens here, if you look at this point, at x equals to 1, suppose P2 x is our 1 minus x square by 2. So at P2 of 1, what will happen? It is actually 1 minus 1 by 2. So this is 0.5, half. But if you look at fx equals to cos x, f of 1, if you write, so cos 1, this will give you 0.54, almost equal to. So this, the gap between is actually almost, they are very close to each other. So that is why, how many points we are getting? So from here, from 0 to, so this many points we get. So this is the interval of, you can see that in this interval, this green curve, that is the P2x. This is a P2x green curve, and the fx, this is are matching their values. Okay. So if we have some unknown function, we'll try to approximate them as with some known functions. So this is the idea of approximation. Okay. Now, as I mentioned, that how do we actually approximate? So these polynomials are called Taylor's polynomial. This P1x, P2x, P3x, Pnx are called polynomial, Taylor's polynomial. Now the claim that we have said that we want to approximate this function by the Taylor's polynomial. So this will be justified now. Okay. So how do we do it? For example, if we take L of x is a function f of a plus f dash of a minus x minus a. So remember the Lagrange's mean value theorem. Okay. So this is the green curve is fx that is given. We don't know the exact formula. So we want to approximate this function at the neighborhood of a. So neighborhood of a, we will try to make it in this form. Now if you try to find out the slope of f of a, the slope of the curve is at a. So this is nothing but the slope of the derivative actually at f of f dash of a. So this will give one good approximation of the function. Now if you try to differentiate this function, this is our polynomial. So this will L dash of L prime of x, because so f of a is a constant value, so this becomes 0, and then f dash of a, and x minus a will be 1. So this is nothing but f dash of a. So what we get, L dash of a equals to f dash of a. So this means that the slope of the linear polynomial, so this is the degree of x is 1. So this is linear polynomial. For example, this is it has some expression like this, 1 plus x type. 1 is f of a, and f dot step a equals to 1, and a equals to 0, and x. Okay. So linear polynomial type, 1 plus x. So if you see that this L of x, the slope of the linear polynomial and slope of the curve at the point A are actually matching. So that means we can say this in this interval, the points of the curve, the points of the given curve fx, and the points and the functional value of this polynomial are same. So we call it a first order Taylor's polynomial. Okay, to fx around the point x. So this is the complete sentence. Okay, a Taylor polynomial, it has to be some around some point. This is a first order polynomial. Now we can say that we want to match as many points as many numbers. So if you try to look at of this form, so if you get a function like this, or if you can get another function of this form, if you say this is a P2x, some polynomial of order 2, that is quadratic polynomial, then what will happen? Can we get such polynomial? The answer will be yes. So this is actually, it is matching over this region. So this many points for x equals to this many point will be taken for good approximation.
Sir, so for e raised to the power x, we calculate, we take a as 0.
E to the power 0, that will be 1.
No, sir. For e raised to the power x, the expansion that we study, for that we take the value of a to be 0, according to this.
Yeah, no, we can approximate some other point also.
No, the
For example,
general that we study is around 0 only, right?
no, not like that. General
Okay.
at point A. See
Okay,
here
sir.
we have approximated x equals to 2. At x equals to 2, we have been approximating the function e power x. It is not necessary that we have to approximate within the 0. It can be any point. Okay. Here it is it is not a is not 0. It is arbitrary point.
Yes, sir. Yes, sir. Got it.
So if we take one quadratic formula, quadratic polynomial, it will have of this form one linear point, one linear coefficient, another will be some quadratic formula. Okay, so a square term will be there. So if you take, we need to satisfy this relation q of a equals to f of a, q dash a equals to f dash a, and q double dash a equals to f double dash a. So look at the structure. Okay, and then we try to find out the C point is a f dash of f double dash of a by 2. So here we can write p2x as the second order polynomial, which is a better approximation to the given function fx. So as you increase your degree of the polynomial, so you will get more and more accurate values. I mean good approximation. Okay. Now, how do we get for nth order polynomial? So for that, we will write. Suppose we have an arbitrary expression like this. So this is a polynomial, okay, where a c0, c1, c2, c3 are unknown. X is our variable and a is any particular given point for where we are trying to approximate the function with the help of Taylor's polynomial. So we want to find what will be the expression for the Taylor's polynomial, which is actually approximated by, fx is approximated by this polynomial. So we want to find out the generalized form of this nx. So for that we want to, let us see that example. Y equals to 3, the slope will be 0. But if you y equals to 2x, the slope will be 2. Okay, so what we do here is actually derivatives. We take the help of derivatives. Now, if you go back and check, for example, this is our f. Okay, now if you take the derivative, if you put x equals to 0, x equals to a in this equation, okay, then you will get fx equals to c0 plus all terms will be 0. 0 plus 0 plus all are 0. Then you will have only f of a equals to c0. So the expression is f of x equals to c0. So in place of c0, we can now substitute f of a. Okay. Similarly, if you take the first order derivative, then from here we will take the first order derivative as, so f dash of x is c1. So since c0 is 0, the derivative of c0 is 0. This is a constant term. Then c1 will be there, and after that 2 times c2 into x minus a plus 3 times c3 into x minus a whole square. So and this will form. Now again we try to put x equals to a in this expression. So there we will get c1 equals to f dash of a. Okay. And now in this way, if you generalize this concept, so f dash of f double dash of x So 2 times C2 into 3 times 3 into 2 into C3 x minus a, and then you will get f double dash of a equals to 2 times C2. So from here you get the C2 value. So in order to find, for example, this is approximation by polynomial x. So this polynomial will be known if you know this C0, C1, C2 and C3 and L and so on. So what we are doing is actually we are trying to find the coefficients, because this will be x, we have to find out, f of x we have to find out, a will be given. So only this unknown is C, these values are C0, C1, C2, all these are unknown. And we are getting this by matching the points of f of x with the help of the derivatives. So here we get C2 equals to this. Now if you generalize this concept, so here it will be, so 3, 2 and 1. So this becomes 3 factorial. Similarly, if you go for the fourth order derivative, then you get 4, 3, 2 and 1. So this will be 4 factorial. Okay. So in this way, so this will actually relate to the values of C3. This will relate to the value of C4. In this way, we'll proceed, and the final expression that we can get, for example, instead of a, for example, if you take a equals to x0, substitute, okay, then you will get the polynomial in this form. So initially f of a, so this is f of a, C0, and then we have C1, f dash of a. So this is the C1 value, okay. Then this is the value of C2. This is C0, C1, C2. This value is C3, and finally we will have this as, so this is Cn and Cn plus 1. N plus 1. So we are taking n plus 1. I think we can extend this also, but we'll stop here because there are some expression. So this is an informal introduction to the Taylor series expansion of a function. Now if you want to define it in a formal way, then we have to go through by definition. So we'll give the definition. But before that, let us understand one Taylor series of f cos x. Okay. Just now we have found that the Taylor series can be written of this form. Any function, this is fx, can be approximated by these expressions, where these are the derivatives where we have to find out. This C1, this is C0, C1, okay, C2, C3, C0, C1, C2, C3, and so on. We have to find out. So for a given function fx is our cos x. Okay, then we try to find out fx, f dash x, then f double dash x, and then f triple dash x, and so on. Then we get that cos x, in place of cos fx, we will write down cos x. So cos x equals to this one. Okay, we are trying to approximate this value at a. So these values we have written. Now if you put a equals to 0, then we will get these values. 1 by these functions. So we have seen, okay, from our school level mathematics, from high school mathematics, we know that cos x equals to this formula. Similarly, we can approximate sin x function using the Taylor's polynomial. Okay. Now, as you have seen that earlier we had f of b equals to f of a plus f dash of c into b minus a. So this is Lagrange's mean value theorem. Lagrange's mean value theorem states that f of b equals to this function. Now, if you want to generalize this function, so generalization is actually the Taylor's theorem. So Taylor's theorem says if, so this is the formal definition of the Taylor's theorem, or you can say Taylor series. If f is a function defined on the interval a comma b such that the nth order derivatives is continuous on this interval and the nth derivative is continuous, it will exist on the open interval ab. Then there exists at least one value. Remember, C can be more than 1. So it is saying that at least one value C such that A less than C less than B, with this condition, it will satisfy f of B equals to f of A into f dash of A into B minus A, then 1 by 2 factorial, 1 by 3 factorial. So this will be satisfied. And of course, up to n minus 1, then nth order derivatives we have written, because nth order derivative will exist. We don't know about the rest. Okay. So that is why we will write up to nth order plus some, okay, we call it a 1, equation number 1. So this is known as Taylor's formula, which will be used to approximate a given function by Taylor's polynomial. So we have seen how we can approximate a given function fx given by polynomial x. We'll change the value of n equals to 1, 2, 3, and so on. Okay. And then we'll find that at some point at x equals to a, the value of f of a becomes the Pn of a. So these values are actually equal. So this is the main idea of Taylor's approximation, and this expression is actually known as Lagrange's form of remainder. Okay, so we'll write what is the remainder term. Okay, for that we need some other expressions. So which is called as, instead of b, we'll substitute a plus h, just slight increment. For example, we have taken a plus b, but we'll try some small amount of increment. For example, we'll take a plus h. Okay. So a small increment if you take, then b minus a will be h. And we'll write the conditions. These two conditions will hold. Okay. And then we will substitute, in place of b, we'll substitute a plus h. Okay. Then f of a plus h is equal to f of a plus h into f dash a plus h square by 2 factorial y into f double dash of a, and so on. And then we'll have another, for example, last time what we have seen, there we have seen one c variable. One c is the number which is within the open interval ab. Okay, now in place of c, what we write? A plus theta h. A plus theta h for theta less than equals to 0. For example, if you write a, this is a and h. Okay. Now theta equals to, since it is less than half, so what will happen? For example, theta equals to 0. Or you can take half. Then a plus theta, a plus theta equals to half into h. So this becomes, for example, this would be helpful if we take some numerical values. So this is 3, and this is 3 plus 1, this is 4. Okay. Then what will happen? So 3 and h equals to 4. Okay. 3 and 4. H will be 1. H is B minus A. This is A, this is B. So H is B minus A. So this would be H equals to 1. 4 minus 3, this is 1. Okay. So if you take in this way, so 3 plus half. So 3 and half, so this is 3.5. So this will be at some point. So what happens, instead of writing this C is in between A to B, okay, if we write C equals to, here C equals to A plus theta H also, then also it will be okay. Because we are restricting the point A plus theta H within the open interval A comma H. So that is why, and this particular term is called as the remainder term after n terms and denoted by Rn. This is remainder term. So because this is the first term, this is second term, this is third, and this is nth term. Okay, and this is n plus 1th term. Okay, so after n terms, whatever the term that is remainder, we call it a remainder after n terms, and it is denoted by Rn. Okay. So in this is this Taylor's theorem. I think it was developed in 17, 15 or some 50s. After that, there was another derivative is there. Another modification is there, which is given by Maclaurin's. So Maclaurin's is actually, so this series, instead of A, we have taken A as arbitrary point. Okay. Okay. Just now, some of you have actually mentioned that whether we have to take always 0, A equals to 0. So if you take always A equals to 0, okay, then the series is called Maclaurin series with Lagrange's remainder. So this remainder term will be same. Okay? The name of this remainder is actually same. The only difference is the name of the series will be changed. Okay. So you can just take it, and you can just let me just make it some bigger. Yeah, so this Maclaurin series is actually derived from the Taylor's theorem. And in fact, if you take n equals to 1, then the Taylor's theorem is actually reduced to Lagrange's mean value theorem. That is why we have mentioned that this Lagrange's, Taylor's theorem is the generalization of Lagrange's mean value theorem. Now, corollary 2, it says if we take A equals to 0 and H equals to X, then the series will become of this form. And this particular series is known as Maclaurin's theorem or Maclaurin series. Okay. Because Maclaurin has given this expression, so in order to give respect, so they have called it Maclaurin's theorem, or sometimes whenever we say Maclaurin's theorem or Maclaurin series, they will be used as interchangeably. So they will indicate the same expression. Maclaurin's theorem, it will have the definition. Okay, if you think about Maclaurin's theorem, so this will have question. It is continuous from 0 plus h. Okay, n minus 1 exists on 0, 0 plus h. Okay, second assumption will be a nth derivative exists on 0, 0 plus h in this interval. Then, okay, then there will be some point at x for theta equals to less than equals to, so this remainder term will be of this form. So these two assumptions will hold. These two assumptions will hold for, okay, instead of a, we'll write as 0. And then we'll write as this form. These are assumptions. This is the final expression. If these are satisfied, then this will hold. So this was Maclaurin's theorem. And then, so how to remember? How to remember the expressions for the Taylor's formula with remainder term? Okay. So it is very funny expressions. Normally we don't actually use this kind of expressions, base point or increment is input minus base point. But this is just for your reference, so that you can take, you use any input, for example x, then base point may be a. So you will took a, f dash a, this is the base point. Input is x minus a. Input is base point is a, because you want to approximate the function at x equals to a. Okay, and then you try to find out, this is a, and in the neighborhood of a you want to find out, this is our x. Okay, so this is our input, whether the function that we want to generate, so this is the polynomial pnx and this is fx, whether these two values are same, that we have to find out. So that is why x is our input point. Okay, so we have to find out some base point, take the interval, the neighborhood, and we will try to find out the values in this point. All the point we will try to approximate. So that is why f double dash a, so the input is x, base point is a. Similarly, base point is a, input is x, then a, and so on. And this c will be some point x minus a. C is in between the point and the input. So this is the base point and the input. Now if you just rewrite it in a different way, then what happens? This is x plus, so input is there, input plus base point. Or you can write base point plus increment, like this one, a plus h. A is our base point, and then the increment a plus h. Okay, if you look at the second expression, here it is. This is base point and the increment is h. Okay, so this is a. The second expression is a plus h. This is a h. Then a. This is a h square. This is a h cube. This is a h to the power n. H to the power n plus 1. Okay, so this is base point plus increment in between the point C. So that is why we can now just summarize this expression of this form. So Taylor's formula with remainder term, this will be our called remainder term. After n plus 1th a. In fact, you don't have to bother about the remainder term is actually the error. You remember the, okay, let me just go through the example that we have seen here. Let me, here, not there. The error that we have seen here, this is 0.54 and this is 0.5. So the error is 0.54 minus 0.5. So there will be 0.04. So error will be this much. Okay. This remainder term that we have seen is actually related to the error function because we are trying to approximate. We are not getting the exact value, but if we get some approximate value also, sometimes we will be happy because exact value will not be available to find out always. So this remainder term is actually associated to the error while doing the approximation. Now there are some examples that you can go through and check. So these are some famous or familiar Taylor's series expansions. Although you have studied this in your school mathematics, but you have to look into a different perspective. The perspective is that now we are trying to see them as approximate polynomials. Because when you will study Fourier series, okay, then any function, then you will see any function fx is approximated by sum of sigma of sin x function and plus sum of cosine x function. Any function can be approached. This is for your information. It is not included in this course. Maybe you will study in third semester or some other time. Okay. So let me just give you one example. So this is our Taylor's formula. We have to find out, write the Taylor formula for the function fx equals to this, and in this interval about x equals to 2. Remember, a will be given with the Lagrange's form of remainder after 3 terms. So you have to this many informations it is given. So what we have to do is, okay, let me just give you. How to do it. So first we have to find out the values of f of a, because we have to see that f of x plus h is equals to f of x plus h times f dash of x plus h square by 2 factorial f double dash of x plus h cube by 3 factorial f triple dash third derivative of x plus, say here, remainder after 3 terms. So this is our first term, this is our second term, this is our third term. So this is our actually remainder. So this will be our called R3. So we don't need to write the rest. So we'll stop here. Okay. Now, if you try to find out the values of f of a, here fx is given. What is it? Log of 1 plus x. Okay. Here x is given as 2. Given. Okay. Oh. Shanmukha Raghuram, he wants to join now. But I think everybody has got their institute email ID. Why they are trying to join with personal email? Maybe they are trying to log in through mobile, and they have at least two email IDs. So while you try to join, please make sure that you join through your institute email only. Okay. So this is our given condition. Okay, so what we do, f of 2 equals to log of 1 plus 2. So this becomes log of 3. We keep it as it is. Okay, next, what we want to find? We have to find fx is given 1 plus x. Then f dash of x, we try to find out, it is 1 by 1 plus x. How about f double dash x minus 1 by 1 plus x whole square? How about this f triple dash x minus, so this becomes plus, so plus of 1 plus x whole cube. So from here we will take f of 2, we have seen that log of 1 plus 2, this is log of 3, then f double dash of 2, sorry, f dash of 2, this becomes 1 by 1 plus 2, so this is becoming 1 by 3, f dash of 2, f double dash 2, so this becomes minus 1 by 1 plus 2 whole square, so this becomes 1 plus whole square, that is 3 is 1 minus 1 by 9, so this becomes f triple dash 2, so this will become 1 by, not 1 by, so this becomes plus 2, so this is 2 by 1 plus 2 whole cube, that means 3 cubes, so 2 by 27. Okay.
Sir,
Right.
isn't f of x log of 1 plus x?
Yeah, log of 1 plus x equals to 2, right?
Oh,
Oh,
yes,
sorry,
sir.
sorry.
You wrote there
Yeah,
f
yeah,
of
right.
x is
Yeah,
1 plus x.
yeah. I have written, yeah, thank you. Yes, right. You're correct. Okay. So while I was doing this calculation, I have skipped. Anyway, thank you for correction. Okay, so these expressions are actually, now it is correct. So what about R3? R3 will be h cube by 3 factorial f3 third derivative a plus theta h. So this is by our definition. Okay? By definition, this is R3. Now, if you just try to substitute these values, f of x, we know that f of a plus, or you can write f of h, sorry, f of x plus h by in fact,
It would be for f of x plus a.
just let us write the first formula, because we want to find out the polynomial. Okay, so if you write it, f of b equals to f of, the expression was f of a plus b minus a times f dash of a. Then a b minus a whole square by 2 factorial f dash of f double dash of a. Okay, and this is R3. We don't need to write other terms, higher terms, because we have to stop after 3 terms. So this is okay. So if you write it as if b equals to x, so this becomes f of a, and a equals to, we have to find the 2. Okay, because so x minus a, the polynomial will be f just a plus x minus a whole square by 2 factorial f of a f double dash of a plus R3. Now put a equals to 2. Okay, so here you will get f of x, it will be f of 2 plus x minus 2 times f dash of 2 plus x minus 2 whole square by 2 factorial. So f dash double dash of 2 plus r3. Okay, so if you substitute this value, f of 2 is nothing but log of 3 plus x minus 2 times f dash 2. What is f dash 2? It is 1 by 3. So 1 by 3 plus x minus 2 whole square by 2 factorial f double dash 2. There it is minus 1 by 9. Okay. So we will substitute minus 1 by 9 plus R3. R3 is, okay, we'll calculate R3. So let us just write log of 3 plus x minus 2, or you can write just 1 by 3. And then, so this is 2 times 9. So minus 18 by times x minus 2 whole square plus R3. Okay, so let us just try to find out what is R3. R3 is x minus 2 whole cube by 3 factorial times, so this is 3, or you can write a triple 1, 2, 3, then a plus theta h. Okay, here a is equals to 2. Theta we don't know. Theta is values 0 to 1. And h is actually x minus 2. X is our required point. Remember, this is a, this is our x. We try to approximate. So x minus a, we call it h. Okay, so here we substitute x minus 2 cube by 3 factorial times f triple dashed a equals to 2 plus theta and x minus 2, h equals to x minus 2. So if you do this, if you simplify it, x minus 2 whole cube by 3 factorial 3, 2 into 1 times f triple dashed 2 plus, okay, 2 theta will be there. So 2 minus, actually, yeah. So this is a kind of 1 plus, you can take triple dash theta of x. Okay, so this is theta. You can take, this is, you can write a and b, f of a plus b type. If you go back and check the expression for r theta, it was this formula. Okay. Now 1 plus x, in place of x, we'll substitute those values. So in place of x, what we have now, just to recall, we have f triple dash x equals to, the value is 2 by 1 plus x cube. Okay, so here we'll write. So this is our x now. This is our x now. And we'll substitute these values. So this is 1 plus, what is x cube? X is this one, 2 plus theta x minus 2 whole cube. Okay. So if you just simplify it, then what will happen? No, here it will be 2. 2 is there. Okay. So these two will get cancelled. X minus 2 whole cube by 3 times. If you just simplify, then it will be 1 by 3 plus 1 plus 2, 3. Then theta into x minus 2 whole cube. So that's what you can stop here. Because R3, you need some expression. So that's it. So this is what we are asked to find out. Okay. Also, try to find out after 3 terms. Lagrange's remainder R3 after 3 terms. So write the Taylor's formula for the function given fx. So we try to find out f dash, f double dash, f triple dash. Then we will evaluate this formula, these values at the point. Okay. And then we write the Taylor's formula after 3 terms. So this is our, not this one. So f of x is actually this one, where, so this is the Taylor's formula that we have been asked to find out after 3 terms. So R3 you can find out in this way, where R3 equals to this. Now there are some more examples, worked out examples are given. So I would ask you to verify. Okay, so this one is actually wanted to show you that if our x is given, then for 1 plus x square plus k times x cube, if we think this as a p and x, then this will be a approximation. Now look at that. As k varies, k equals to 1, 2, 3, 4, 5, 6, 7, and these two curves are actually matching each other. The gap is becoming 0. So I would recommend you to verify. If you can verify this, then these are your, then you will understand. A practice problem will also be there. If you find any kind of mistake, of course, you have to inform me. I have already included and verify these results. So that's it for today. I will give you for some practice problem. I will find out and then I will include some practice problem and then I will share this PPT. If you have any doubt, you can ask me.